This is the next problem on the unit 5, that is equilibrium, right? So this problem is interesting. You can pause the video and read it and think. So you can see that in this problem the only data that is given is weight of these tubes, right? They are side view of the tube, so it's circular, it's tube, and you can imagine the pipes are laid like this. So the weight of each tube is given, right? And nothing else, nothing else. And what you are asked? You are asked to find out the forces at all the contact points. Okay. So what are the contact points or contacts? What are the contact points? So you have, let's say, A, B, C. This is D. Here it is E and F. Right. So these are all. So we want to find out force at B, A, C. That means contact point between these two tubes, between these two, and contact point with the tube mixed with the vertical, right? So these are the forces which we want to find out. Now let's just pay attention to few things. Point number one is our task is to first draw the direction of forces, and then the forces which are not horizontal nor vertical, we want to find out the angle these forces make with the horizontal. That's all, right? That is first. Secondly, let me ask you a question, because we have discussed this the normal forces in many numericals, many videos, if not numerical. So look at this. There is going to be a normal force from this surface, and all the surfaces are smooth. That means there is no friction involved. So the force will be always perpendicular to the normal surface, perpendicular to the surface. So if this is a surface, there is going to be normal force. And will it be equal to weight of the cylinder? Will it be equal to weight of the cylinder? Think about it. This weight will be downward, and the normal reaction from the surface, will it be exactly equal? Okay, so I hope you have paused the video and thought about it, right? So the thing is, it's not. Why? Because see, this tube is also sharing some of its weight on this. This tube is supported by this tube and this tube. That means part of this weight is transferred here, and that is also to be considered while you consider the normal force, right? So the normal force is balancing the weight of this and the weight component of this, which is shared by this tube, right? So similarly here, I just wanted to, so normal force, don't really quickly say that this is equal to the weight of the tube. No, you have to consider the other forces on this tube in order to consider normal force at point B. Anyway, so let's draw the free body diagram. That means let's draw the direction of forces. See, at point A, if I say this is, and I'm going to draw the free body diagrams of these tubes, okay? So this surface is going to push this towards right. Normal force, reactive force from this surface is going to be towards right, okay? So your force is going to be, I can say it in this direction, and I can take it in this way. So okay, so this is, I can say this. So this is RA, okay, RA. What about, there is going to be a normal force here, right? So this is RB. Then what about this point C? See, at point C, you will see that this circle, upper circle, is going to exert some force on this, and this is going to exert equal and opposite force on this, right? So that means there is going to be a force in this direction, and there is going to be the same line. If I have not been able to draw very good circles, it's a very smooth board, I hope you tolerate this. So there is going to be equal, and I'll call this RC, right? These forces are RC. They are equal and opposite. I hope this is, it has to pass through the center. They should have been exactly in the same line. Just accept this. It's very difficult to draw the correct diagram here. Okay, so this is RC, this is RC. They are equal. Fine. Then you have a force here, right? Similarly, the force will act. This tube is going to act on this. That means a force in this direction, right? So the force is here. I'll call this RD. Okay. Similarly, a force in this direction. This is RD. Sorry. RD. Okay. Then we have got weight here. So we will consider weights. All the weights. This is 8 kilonewtons. Each of them is 8 kilonewtons. Each of them has got weight equal to 8 kilonewtons, and there is, I will draw it here, 8 kilonewtons. One and the same, on the same line. Okay. So obviously there is going to be upward force, and I am drawing it here. Upward force reaction from this, which I am going to show here, which is RF. Please understand this. I can show it RF here or here in the same line. I have shown weight downward and reaction upward. I have shifted it upward here. Here I have shown reaction here, so I am showing weight here. It hardly matters. It should be in the same line. Okay. And then of course there is a reaction from E. Right. This surface will give a perpendicular. The force will be perpendicular to this surface toward the center, and I have explained why toward the center, because these are tangents in a way, and perpendicular drawn to tangent will pass through the circle. So I am showing this force here, right? So this is RE. This is RE. Now, see how many forces are there which are not vertical or horizontal. The forces are 1, and this is the same, right? And the other force is this and this, right? So essentially, you want to find out the angle these forces make with the horizontal. It means, if you look at it carefully, you want these angles, right? If I join this, you want these angles, right? So how do you find out these angles? Now you can see that, how do you find out the angle RC, RE, then RD, okay? This is RD, and RC. Basically RC and RD, right? RC and RD make with the horizontal. That's what we want to find out. And then the problem, it's just simple. Then you can solve it mechanically. So to find out this angle, and that's the crux of the problem, is you have to pay attention to the structure, how the pipes are placed. You can see that a line joining the center of these two tubes becomes tangential to this tube, okay, is tangential to this tube, which means, and I'm just just clearing this off so that you can understand this point, right? So this is the point. So if you join these points here, right, okay, so look at this, and if you draw a line here, so you have a triangle, and this is half of that. See, look, you are not given any dimension, but what you can immediately find out from this is this length is double this length, right? This plus this, because all the circles, all the tubes are similar. That means this is the radius, this is the radius, this is the radius, this is 2r, this is r, correct? So if you want to find out this angle, let's say angle theta, sine of theta is equal to this opposite side, right, upon hypotenuse. If this is r, this is 2r. So this is going to be r by 2r, which is half, right? So theta is 30 degrees. Theta is 30 degrees. That's all. So this is 30 degrees, this is also 30 degrees. That means RC and RE are making angle of 30 degrees. Then our task becomes simple. All that you have to do is you have to resolve the forces for each of these circles in horizontal and vertical direction equated to 0. Correct? Why equated to 0? Because this is under equilibrium. Okay. I hope I don't have to do the resolution, but let's do only one case. And so we have found out angle 30 degrees. Now let's consider first sphere, first tube, right? And let's say sigma fx. We are going to write down the expression for sigma fx and equate it to 0 because all of them are in equilibrium. So what is this? Is Ra is towards right. Ra is the normal reaction from the vertical surface. So Ra, okay. Then this vertical Rb and this downward force will have no bearing on horizontal. But Rc is in this direction, right? And when you resolve it, so this is going to be Rc cos theta. Rc cos theta. And if you look at the arrow, it is going to be towards left. So I can write this as Rc minus cos 30, right? And is there any other force? There is no other force, right? So this is equal to 0. This is first equation. Then let's consider, we are considering circle, the tube 1. So sigma Fy. What is sigma Fy? This is 8 kilonewtons downward, so it is minus. So let us resolve the force in vertical direction. That means for this tube, we'll also say sigma Fy is 0, right? So let's say sigma Fy. I'm considering the forces on these tubes. So sigma Fy. What are sigma Fy? One, there is normal reaction which is upward, right? And so it's positive Rb. Then Rc will have a vertical component. This is theta, and Rc sine theta will be vertical. And look at this direction. This is the force coming from this tube, so it's toward the center. When you resolve vertically, this is going to be negative, right? Downward. So this is minus Rc sine 30 because theta is 30. And then you have the weight, 8 kilonewtons, which is downward. So minus 8 is equal to 0. Now, in this way, you can write down two equations for this, two equations for this tube, except that here I had, you have to consider the weight of this tube, which is acting downward, 8 kilonewton. So what are the forces on this? There is going to be a reaction from this in this direction. So I'll show this direction here. So this is your RC, because this is your contact surface C, RC. Similarly, there is reaction from this, right? And this is D, so I'll say, you can show it here if you want, RD, right? So we clean this. So RC, RD, weight, these are the forces. Similarly here, it's a weight, the normal reaction at point F. Then this is going to produce horizontal, this is RE, and the action of this tube on this is RE. We can say, I'm showing it here so that this is E here. So this is RE. Okay. So you write down these two equations for these tubes, total 6 equations, and it will be easy to solve this. So basically this is a method. The central point was to settle the geometry, that means to find the angle theta, and that was the most important thing because no dimension was given, only weights were given. Thank you.